So the first part of this about the camera matrix, this is what I had posted earlier. So that contains the description of the intrinsic parameters, extrinsic parameters, then considerations or the parameters that come in due to the pixel coordinates, and the finite projective camera and general camera models. So, uh, I mean, we can quickly go over these things again if you have a question. Else, I can move on to this. This is what I want to talk about today: anatomy of the camera matrix, and then camera calibration and some data normalization part. So, are these things clear? Like, if you had a chance to look at the post-it notes and the earlier recording, then do you have any questions about what was done in these notes? Because this, I, I'm sorry I couldn't do this live, but this is extremely important. Okay. Your whole understanding of camera calibration is based on the understanding of what are the intrinsic parameters, extrinsic parameters, and how finally we get this camera matrix. Okay. Because if you are ever in a situation where you have to do some camera calibration, even to use OpenCV's built-in function on camera calibration, which you will do in one of the exercises, you need to have an understanding of these things, okay, to apply it to a given situation. So if you have some questions, you can ask me now, else I can move on and you can ask me later. There was a small mistake here in counting. So I had counted 9 before, and because I added 3 without thinking, so that single F has now become alpha X and alpha Y. So really we are only adding one more. So it shouldn't be 12, it should be 11 parameters. Okay, so that is how. So there is this little correction. Okay, and then if you have so this was the important thing towards the end, that first of all, if you start with the camera, this is the camera matrix, and on the other hand, you could start with any 3x4 matrix in which the first 3x3 part is non-singular. Okay, and then is that can you express that, or will that matrix be the camera matrix of some finite projective camera? So you can ask this converse question, and this was an attempt to answer that. Okay, so indeed you can do that. Okay, what you will require to do is, so if you're starting with a matrix, you want to write it like in this form first, right? So you want an upper triangular matrix and a rotation matrix, and then you have any hope of expressing a 3x4 matrix as a camera matrix. So that is what was explained here, that you can do so by taking the RQ matrix decomposition. Okay. That was this whole thing. And so in general, there are these other camera models, okay, apart from the pinhole camera model, which leads to the central projection. Okay. There are some other central projection, your finite projective camera. Okay, so the leftmost case, that is the case of your regular camera. Okay, so for a regular camera, you're in this leftmost case. Okay, but you can also have that M being singular, which corresponds to having a camera at infinity. Okay, so this is not your regular camera. Okay, but theoretically, you can talk about cameras like this. Okay, so as I was saying earlier, this one kind of camera at infinity, which is called the affine camera, which maps points at infinity to points at infinity. So one of the examples of that is a weak perspective camera, where the scene relief is small, and we discussed all that. Okay. So, and this non-affine cameras, this is some part that I'm not going into at all. Okay. So, but you should just be aware that you could start with any 3x4 matrix and call it the camera matrix of a certain general camera. Okay. All right. So are there any questions? If you don't say anything, I'll assume there are no questions and move on.
Ma'am, an email was sent to you last night about like a request from the class to go a bit slower and etc.
Yeah, so I read that email, but I don't have much to say about it. First of all,
Okay.
I have said that I will not be having 3 lectures like this throughout the semester. This is for the first few weeks, and this is from my experience of teaching this in the last semester. That if I don't do this, you can see how many things we are still doing image formation. Okay, and we still haven't touched 2 view geometry. This is single view geometry. You're talking about one camera. Then there is 2 view geometry, which at least we should touch, if not do details about. And then we will go into digital image processing, which you will see when I listed the syllabus, it's the early level vision. Okay. When I taught this course last time, I could barely finish some topics in mid-level vision. Okay, and I couldn't even go to high-level vision at all. So even if I hope to finish all the planned topics in mid-level vision, which will make this a little bit more than a digital image processing class. Okay, if you want to call this a computer vision class and not a digital image processing class, then there are some number of topics that I should cover. Okay, and if I hope to do any of that, then at least in the beginning, I'm going to require you to put in this extra effort. Okay. I mean, I could also, instead of having detailed notes like this, I could do those slides. I have slides ready, okay, in which I can cover all of image segmentation in one go, or all of, histogram processing in one go. That is also fine. That way, I'll be doing 2 lectures per week and covering, as much as possible. But I don't know how much you will learn that. So I mean, if one has to do things in so much detail, then I'm going to take some time. And as I said, I won't be able to do this all semester anyway. Throughout the like maybe in the first 4 or 5 weeks, I'll be doing these 3 lectures, so that once we get started with some basic image processing techniques, then I can slow down. Okay. So yeah, I'm sorry if you are not able to match the pace of this class, but this is how the pace is going to be if we want to call this a computer vision class. Otherwise, this is going to be just an image processing class. Okay.
Ma'am,
Yes.
also with the assignments, ma'am, can the deadlines be on weekends? Like it would be very helpful for us.
Yeah, I can. So right now, I have given you something that you just finished. From the next assignment onwards, I can make it so that the deadline is a week. Okay.
Okay.
Yeah. So coming back to the topic at hand. So there is a little bit to be talked about the anatomy of the camera matrix. What do I mean by anatomy of the camera matrix? What I mean here is the suppose you are given any 3 by 4 matrix P, and you're told that this is the camera matrix of something. From that 3 by 4 matrix, how do you find out the properties of the camera? Like where was the camera center? Okay, what was the principal axis? Uh, what were the images? Okay, of the coordinate axis of the camera. Okay, so these kind of things. So from the matrix, you can find out these things. And so this study, I'm calling the anatomy of the camera. Not me, I mean, the book also calls it anatomy of the camera matrix. So now, this is the only information we are given. We are given P, which has a 3 by 3 M here. And so this is a 3 x 4 matrix in the end. And this matrix M is of rank 3. Okay. So full rank matrix here and additional vector P4. So given this matrix, how do you find the camera center? So the point of the camera center is that since this whole matrix is going to be a rank 3 matrix, P is going to have a one-dimensional null space. Okay. So now suppose that null space is generated by some vector C. Okay. This means since C is in the null space of P, this means that PC is 0. Okay. So my claim now is that this C, which is the generator of the null space of P, that C is the camera center in homogeneous coordinates, of course. Okay. So let's prove that. So suppose A is some point in space, okay, and C is our vector, which is the generator of the null space. Okay. You consider the equation of the line that joins A and C. Okay, parametric equation. So this is the, so I can write it as xt is Ta plus 1 minus t times C, where t varies between 0 and 1, right? So if you take t equal to 0, that is going to give you the point C. T equal to 1 is going to give you the point A, and for other values of t between 0 and 1, you will get intermediate points on this segment. Okay. So this is, so now what happens when you apply P to this? Okay, if you apply P, which means your camera matrix, to this segment, the result is also going to be a segment. Okay, so a line segment. So what I'm going to, the notation here is that under the mapping x equal to px. Okay, where do these points capital Xt go? So they are projected to points small xt. Okay, so this is p of Ta plus 1 minus Tc. Okay. Now remember that we said that this P is not a linear map. Okay, so this is just a projective transformation. So this is not linear. However, the fact that it takes collinear points to collinear points, any projective transformation, that's the definition, right? If the projective transformation takes collinear points to collinear points, and that is why this is going to go to T times Pa plus 1 minus Tpc. Okay, so this is not the linearity property. This will happen because this is true for any 2 points as close as you want. Okay, but Pc is 0. So what this means is that xt, small xt, is T times Pa for all t. Okay, so this set of all points Tpa is just one point because these are just scalar multiples of the point Pa. So this is just one point in homogeneous coordinates. Okay. So what it means is that all points on that array, okay, or all points on this segment are mapped to the same point P. Okay, and the only point in with respect to our setting of this camera is the camera center. The only point satisfying this property. You could do this for any other A. Okay. So if all these rays are passing through C, then that means that C has to be the camera center. Okay. All right. And this xt that you took here then was the ray through the camera center. The question now is how to find this C. Okay. So since M is, if you're given M is non-singular, then you can just take M inverse P4 1. Okay. So you apply M inverse to P4 and you adjoin this 1, and you can check that P of this is going to be 0. Okay, so see, this vector will lie in the null space of P. On the other hand, if M is singular, okay, then you take C to be the vector D comma 0, where D is just any vector in the null space of M. Okay, M is singular, so it is going to have a non-empty null space. So you take any D in the null space of M and form C like this. This will also fall in the null space of P, and the whole theory works. Okay. So this is, later we will see that you can actually give a formula for the camera center in terms of elements. Okay. So given this any P like this, we have seen what the camera center should be. Okay. It should be the vector that spans the null space of P. Now, you can give a sort of geometric interpretation to the column vectors of P. Okay, they have a geometric meaning as as particular image points. Okay, so for this we notice the following. You notice if you apply your matrix P to the vector 1 0 0 0, what you will end up is with the first column of P, right? And so on. If you apply P to this vector, you'll end up with the second column. If you apply P to this vector, you'll end up with the third column. Okay, but then what are these points? So you're applying P to what points? These points are exactly the images. So these points are exactly the axis in the world coordinates, right? X-axis, Y-axis, Z-axis of the world coordinate system. And so if you're applying P to the x-axis of the world coordinate system, you're getting the first column of P. If you're applying P to the y-axis of the world coordinate system, you're getting the second column, and so on. Okay, so in this way, the first three columns of P can be interpreted as images of the world XYZ coordinate axis. Okay, and what about the fourth column? The fourth column you can think of as the image of 0001, but 0001, this homogeneous point corresponds to the inhomogeneous point 000, which is the origin in the world coordinates, right? So P of this, which is the fourth column, that fourth column of P is the image of the world origin. So in this way, you can give a sort of geometric interpretation to the column vectors of P. Is this clear? Similarly, the row vectors of P also have a geometric interpretation. Okay, so suppose I write the matrix P with these elements, and the first row I call P1 transpose, second row is P2 transpose, third row is P3 transpose. Okay, so we just expressed P in this way. Then first of all, remember this definition from maybe the second lecture or something. The principal plane is the plane which passes through the camera center and is parallel to the image plane. Okay, so that picture is here. So this is the camera center C, and this is the principal plane. And later we'll talk about the principal axis, which is the axis which is parallel to the principal plane and passes through the camera center. Okay, so we want to talk about this a bit later. This is perpendicular to the principal plane, passes through C, and is called the principal axis. And the point where the principal axis meets the image plane is called as the principal point. This here is the image plane. Okay. Now you can think of, so when you take a picture with a camera, what points in the world space are going to be imaged on the image plane? So the world points consist of all points around the camera, correct? So in particular, if you consider it with respect to the principal plane, the world space is divided into two parts. Those points that lie on, say, this side, okay, on the left side of the principal plane, left and right are just for convenience I'm using now. So points that lie on the left side of the principal plane, points that lie on the principal plane, and points that lie on the right side of the principal plane. Correct? So the world space is divided into these three pieces. Now, the points on the right side of the principal plane, those are the points that you are hoping to map onto the image plane. Okay. Now, if this image plane was infinite, okay, then in fact, all the points on the right side of the principal plane would be mapped onto this image plane. Correct? The points on the principal plane itself, where do they go? That means the point, the plane on which the camera center lies. Do you see them mapped somewhere?
They all will pass through C itself.
So first of all, light rays from this, when they pass through C, okay, so light rays on the same plane, when they pass through C, okay, they are probably, so, I mean, in theory, what we'll say is they are mapped to infinity on the image plane. Okay. So,
Map to
but what?
infinity, you mean when it is falling out of the, I mean, can you repeat the map to infinity part, ma'am?
So when, so if you have a point on the plane itself, which is passing through C, okay, and you want to talk about the image of this point, then theoretically we are going to say that this point is mapped to infinity by P.
Okay, that
Okay.
means it never
So
fell
in
on the image plane.
yes, so
Okay.
we are assuming that both these planes are sort of infinite. Okay.
Okay.
But really, you don't see the image of these points, right? You will not see the image of these points at all. So a way of expressing that is to say that these points are mapped to infinity. And as to the points in the world space that lie on the left of this principal plane, those are not going to be mapped onto the image plane at all. Correct? Because light rays going from, say, this point will pass through this and go to the other side. Correct? Whereas your image plane is placed on the left of the principal plane or the camera center for now. Correct? So you'll have a virtual image here, but we are not interested in that. Okay. All right. So what I wanted to say is, so this plane, the principal plane, you can express as the set of all those points such that P maps those points to the line at infinity on the image plane. Okay, sort of the horizon of the image plane. Okay, so for this reason, we can make this definition. Okay, so now we write this in terms of homogeneous coordinates. What does this mean? The same set can be expressed as the set of all x such that Px, so Px is line at infinity on the image plane. But what are the points that lie on the line at infinity on the image plane? Will be of the form, the first component is free, the second one is free, you can have anything here. The third component is 0. Correct? So points of this form are points at infinity on the image plane. Correct? So finally, we have got sort of hold of points on the principal plane. Okay, and now we notice that Px is going to be of the form xy0 if and only if P3 transpose x is 0. Okay, so what is P3 transpose? So P3 transpose is this P31, P32, P33, P34. Okay, if that applied to x is 0, then you will have Px to be of this form. Correct, because the third, so when you are applying the matrix, so you have P1 transpose, the first row of the matrix, second row of the matrix, third row of the matrix, that being applied to the point x, y, z. Okay, let me call this something else, a, b, c. Okay, and if that is to be sent to something, and 0, then that means the third element applied to this vector should be 0. Correct? But that third element is P3 transpose. So that's all I'm saying. Px is going to look like this if and only if P3 transpose x is 0. Okay. That's because of this. Okay. And so I'll just clean this up. And so what does this mean? So you have now expressed this plane with this equation. It is a set of all points such that P3 transpose x is 0. That means this is sort of the normal vector. Correct? So once you know the vector P3 transpose, you know the equation of this plane. That is usually how the equation of a plane is expressed in terms of the normal vector. Correct? So the third row of the given matrix P is the row that tells you what is the principal plane of the camera. Okay, so P3 transpose is the vector that represents the principal plane of the camera. Okay, so far what did we see? We saw that once we know this matrix P, we find first the vector that spans the null space of P, that is the camera center. The columns of P we have interpreted as images of the world coordinates, and the third row we have interpreted as the normal to the principal plane. Okay. Now, similarly, you can interpret the first and second rows also as vectors that will give you the other two planes of the camera uh, in the camera space. Okay, so here you have C, which is like this, right? Let me draw it better. So here you have C, X, Y, Z. Okay. This is usually how it is taken, right? So we have defined this plane, correct? We have described the principal plane, but there are two more planes in the space. This is three-dimensional. There are two more planes. Okay, there is with this nomenclature, we have described, say, the XY plane. Okay, but there is still the XZ and the YZ plane. Correct. Those two planes, so will be represented by the first row and the second row of P. For these reasons, because just like we had this equation here, okay, just like we have this relation. Similarly, P1 transpose is going to send a point to 0 if and only if the first component of the resulting vector is 0. Correct? Saying these two things is the same. But then what is this? This is going to be the y-axis in the image. Okay. So similarly, we have this. Okay. P2 transpose x is 0 if and only if this second component is 0. Okay. So in the image, this means the x-axis. Okay. And so on. So in this way, the three rows give you these three planes. The third row gives you the principal plane, and the first and second rows give you the remaining two planes in the camera coordinate system.
Ma'am,
Yes.
the current definition that P2 transpose defines a plane which is mapped to the x-axis of the image and passes through the camera center doesn't make it fixed, right? I mean, it could be attached to the x-axis, passing through the center and still rotate.
Sorry, can you say that again?
I'm saying the definition that you have written, that it defines a plane which is mapped to the x-axis of the
Yes.
image and passes through the camera center.
Yes.
What I mean to say is that then this definition doesn't make that plane fixed. I mean, it
Yes.
could be attached to the
Yes.
x-axis, but
That's,
still have a rotation. Degree of
that's
freedom.
right. So okay, so the only thing fixed here is the principal plane. Okay, if you fix the image plane, then the principal plane is also fixed. Okay, you want these two to be parallel. So this is somehow, the principal plane is somehow fixed when you fix this picture. But yeah, the other two planes are not. Okay, so the other two planes have a degree of freedom so it is not tied so strongly to the image plane. Okay, so the principal point, coming to the principal point, I defined the principal point as it is the point at which the principal axis passes through the image plane, okay, or meets the image plane. That's the principal point. So just we have seen that the principal axis is given by, okay, did we see this? We saw this, right? Because what is the principal axis? The principal axis is perpendicular to the principal plane, and we just saw that the vector perpendicular to the principal plane is P3 transpose. Okay, so that is why we are saying that the principal axis is given by P31, P32, P33 transpose. Okay, and suppose it meets the no, not suppose. It will meet the image plane at this point. Okay, because this is the point on the principal axis at infinity. Okay, now you apply P to this. Okay, so then you get, so applying P to this, really what matters is, so remember how P is? P is this matrix M 3 by 3 and a fourth vector P4. Okay, so if you are applying it to a vector whose fourth component is 0, then it's essentially same as just applying the first 3 by 3 matrix. Okay, So applying P to this is same as applying M to whatever this vector is. This vector in the matrix M is M3 transpose. Okay, so M3 is the third row of M. Okay, so say these two things are the same because the matrix P looks like this. Okay, and so this gives you your principal point. Okay, and then the thing to be decided is what is the direction of the principal axis. Okay, so I mean, you have two directions in which you can take the positive, right? You can decide that the positive of this, the positive side of this is this way, or you can decide the positive is this way. Correct. So there is just that little ambiguity in deciding how should the or which side the vector should be pointing. Okay. So since P is defined, so remember that P is just P is a homogeneous matrix. Okay. So since P is defined only up to sign, okay, there is an ambiguity about taking M3 or so this is not M cube, this is M3, right? The third row of M3 or minus M3 as being the front of the camera. Okay, to point to the front of the camera. So front of the camera or is the world space that is mapped to the image, to the front of the camera. Okay, and the front of the camera is usually considered as the positive direction. So we just have to make a choice of plus M3 or minus M3. And a natural choice to resolve this ambiguity is to take the vector determinant M times M3. Okay, so natural choice is to take the principal ray or principal axis being represented by the vector V equal to determinant M times M3. Okay. There are two reasons for this choice. Okay. So, or I mean, you can observe that in two simple or two cases, this choice sort of makes sense. Because suppose you have the simple cases where you are just projecting from a point in the camera coordinates to the image. Okay, so there is no, I mean, there is no rotation matrix here. Okay, so this part is missing. It's only Ki0. Okay, so that's this simpler case. In this case, your M is going to be K times this I3 cross 3. Okay, and so the third row is just 0, 0, 1 transpose. Or sorry, well, M3 transpose is the third row. So M3 is 0, 0, 1 transpose. Okay, and now if so this choice is good under projective transformations because if a point P is mapped to a scalar, okay, so if P goes to K times P, then with this definition, your V will go to K raised to 4V. Okay, and so because of this K raised to 4 even power, the sign is remaining unchanged. Okay, so what this means is that a scalar mapping of the point is not going to change, or all points on the same line are going to have the same sign. Okay, so this is basically the sign remains unchanged if you make this choice. Okay. And in the general case, when you're taking a point from the world coordinate system to the image via P, then you also have to take into consideration this r. Okay, actually not 0 in this case, right? There is a minus c tilde in this case. This is the most general case of the camera matrix. But in this case also the same thing works, the same logic will work, because the only difference that will come about is because of the determinant of r. But the determinant of r is positive. Okay, so again, the sign change in V is going to be scale invariant. Scale invariant means exactly this. If you take any scalar multiple of P also, the sign is going to remain unchanged. Okay, so taking V to be the determinant of M times M3 is a good choice of sign for the principal axis. Okay, so we are not saying plus or minus, we are saying it depends on the determinant of M. Decomposing the camera matrix. So as I said earlier, we actually can give a formula for the camera center, okay, in terms of the matrix P. So for this, just notice this one property. Okay, so what I've written here is you have any point x1, x2, x3, x4. Okay, so this is a variable point x1, x2, x3, x4, and down here are the rows of P. Okay, so now I have got this 4 by 4 matrix. I just adjoined this vector x1, x2, x3, x4 to the matrix P. Now the determinant of this 4 by 4 matrix is 0 if and only if Px is 0. And so what we can do is we can make a particular choice that sort of satisfies this equation. This is the determinant, right? What I'm writing here is the determinant of this matrix. So x1 times the determinant of this 3 by 3 matrix minus x2 times the determinant of the first, third, and fourth columns of P, and so on. This equation is 0. Okay. And so you can just take these 4 numbers to form your vector C. Okay. Because this is going to make sure that this determinant is 0. These 4 choices. Okay. So you simply take C to be this vector, and then that is your camera center. So given P, this is how you can actually calculate. So remember, what this C had to satisfy is that it would span the null space of P. And what we did by this computation is just found one candidate that spans the null space of P. That's all. Okay. All right. And then you can also find the internal and external parameters. When you're given P, you can find the internal and external parameters by doing the RQ decomposition, as it was described earlier in the earlier lecture. Okay. So once you do this RQ decomposition, you will get this upper triangular matrix R. On the diagonal, the elements that you see on the diagonal will give you the scaling in the x direction in pixel coordinates, scaling in the y direction, and this component here will give you the skew. Okay, and as I remarked in the previous lecture, this skew factor is almost always 0. Okay, and so if you are doing camera calibration and if you see that you're getting a non-zero element here, you should dig deeper about why you're getting this non-zero. So it is highly unlikely that your skew factor is appearing because this angle is not 90. Okay, it can happen because of other reasons which can be again taken care of at the image taking stage. Okay, so maybe the image is not being taken properly. That is one reason why this, or another reason is simply that the camera is very cheap and maybe then it was not using good components. Okay, so yeah, so anyway, so this has to be almost 0. You will never get an exact 0, as you have seen in numerical linear algebra. Getting an exact 0 in all these computations is not possible. So, but should be almost 0. Okay, and the point that you will get here, x0, y0, 1. So this x0, y0 will be exactly be the coordinates of the principal points, right? Yeah. So that is that finishes, I think, the anatomy of the camera matrix. If you have any questions now, you can ask, or if you go through this once and then if you get stuck and you have questions next time, you can ask next time also. Does anybody have a quick question for now?
Does do any of the references have the same sort of notation and writing that you're using in the lectures?
Yeah. So actually, I have written it up here, and I will post it. Yeah, these are sections of the book multiple view geometry that I have posted in the book folder. Okay, so multiple view geometry. In some cases, I have simplified notation, but otherwise, mostly the same notation as in this book. Okay, by Hartley and Zisserman. So I've actually also written down which sections these are from. Okay, so you can take a look at that also. And in any case, if you have a question, you can ask me next time. Yeah, so this some of these things you do need to know, because when you are given a 3x4 matrix P like this, and okay, so if you're given a 3x4 matrix P and told that this is the camera matrix of something, okay, then how do you glean information from it? Okay, how do you say, okay, just given this, you have a 3x4 array of numbers. From that, how can you say what components of the camera setting are hidden in this matrix? Okay, so that is why we need some understanding of all this. At least you should be able to find out the camera center, the principal point. Okay, because many times you require the principal point for data normalization. You might want to make sure that the image center is at the principal point. Okay, and stuff like that. Okay, so you need to have some understanding of this anatomy. Okay, and also that you can do this RQ factorization. Where is that towards the end? That you can do this RQ factorization and get this. So actually, if you in OpenCV there is a camera calibration tool. Okay, so there's a function that does camera calibration for you. Okay, and what it spits out is a matrix like this. Okay, so it will just give you a 3x3 array of numbers. You have to know what those entries mean and what is expected there. Okay, so and it will also give you some distortion factors for the radial and tangential distortion. Okay, so you have to know what those numbers mean and how they can help you. Okay. You by the way, you will have an in the next homework you will have a chance to use that function in OpenCV. Okay, I will guide you through a camera calibration example. Okay. All right. Finally, the process of camera calibration, or this is also called as resectioning, is the process of coming up with the camera matrix, okay, from some number of matching points. Okay, so this is almost like homography, what we saw before. Okay, so if you have some pairs of matching points, small xi and capital Xi, okay, capital Xi are world points, small xi are image points. If you have some number of matching points, you want to find the camera matrix P that maps all these capital Xi's to the corresponding small xi's. That is the question, that is the problem. Okay. And all you know is that your P has to be a 3x4 matrix. So your P is going to be expressed like this. Okay. I think I should have a because this is the same, probably the same mistake that I made last time. Maybe I should have a P1 transpose there. So I think it has to be P1 transpose, P2 transpose, P3 transpose. Okay. But okay, so modulo that one possibility. So your P consists of these three rows. Okay, and each correspondence is going to give you a set of equations. These are the same, these arise in the same way as they were arising in the homographic case. Okay, So again, you notice that the third equation is a linear combination of the first two, and you get rid of that one. Okay, and so you get this equation. Okay, now if you have one correspondence, you are going to get two equations like this. Correct? So, but how many parameters do we have in this P? This is a 3 by 4 matrix and it has all the intrinsic and extrinsic parameters. So how many parameters does this P have? 11, right? We
Yeah,
saw there
with
are
the degree
11. Yeah. So there are 11 parameters or 11 degrees of freedom. Okay. So now if you want to estimate those 11 parameters, how many such? So these are only two equations from one pair of matching points. So how many pairs of matching points will we require? 6 will give you 12 equations. So to be very strict, 5.5 correspondences are sufficient. What do we mean by 5.5? 5.5 means that if you have 6 correspondences, from those 6, the last point or whichever one point, you can use only one equation, that will be enough. Okay. So you need not use both the equations. If you use from the 6 correspondence just one of the equations, that information is also enough. Okay. So, but in practice, we don't do that. We simply take all 12 equations. Okay. In general, if you have 2n such equations, then we just stack them as a 2n cross 12 matrix. Okay. And then we solve for AP equals 0. So we form this matrix A by stacking up all these equations. So two equations from the first correspondence, two from the second correspondence, two from the third correspondence, and so on. Correct? So each time this is going to be a 2 by 12 matrix. Right? So 2 by 12, 2 by 12, 2 by 12, and so on. These are 6 correspondences. Then you will get a 12 by 12. But if you take n correspondences, you will get 2n times 12. Okay. So you form this matrix which contains all this. So that's the matrix A. You solve it for P. If you're taking n to be more than 6, this will be an overdetermined system which can be solved by least squares. Which means you find P such that norm AP is minimized. Okay, and that is typically what is done. Okay, so the minimum number of equations that we require is 6. Sorry, minimum number of correspondences we require is 6. Okay, but in practice, the more number of correspondences you have, the better it is, because you will be using a least square method to solve it. Okay. Yeah. So yeah, we need 11 equations, that is 5.5 correspondences. So this will have an exact solution if 11 equations are known, and which can be done by Gaussian elimination. Okay, but normally what is done is you take more than 6 correspondences and you minimize norm AP with respect to the either the algebraic error or the geometric error. Okay, so in this algorithm there are some finities which you may or may not look at. Okay. Uh, yeah, so you can just think of that earlier case of homography where you were minimizing norm AP with respect to norm P. Okay? And now because this is a 2n by 12, so this has to be 12 by 1. So then that means that these are actually the rows of, which means that, yeah, I should be taking P1 transpose, P2 transpose, P3 transpose, because this will be the first, and then P1 will be the column. P1 will be the first row written as a column, right? Yeah, so P is this, and then I have this. So then this will be a 12 by 1 vector. Yeah. All right. Yeah. So, so what happens is, well, historically, in order to find these calibration correspondences, okay, these matching points, there used to be a very elaborate setting, okay, called the calibration rig, Okay, so you can look it up. I will give you a reference in the book where there's a picture of a calibration rig, and the whole process was very, it's quite technical if you want to go do it with that kind of accuracy. Okay, but more recently, Zhang, so there is this Zhang's algorithm or Zhang's method, which is used most commonly, uh, who showed that you can actually use a checkerboard pattern for camera calibration. Okay, you don't require such an elaborate uh, calibration rig or that 3D object for calibration. You can just do it with a checkerboard pattern. Okay, so this is what we will be doing when we do the camera calibration exercise using checkerboard patterns. Okay, and we will use Zhang's method. And in fact, uh, most of the well, in OpenCV, definitely the camera calibration code uses Zhang's method. Okay, and in MATLAB also, as far as I know, the common calibration toolboxes use Zhang's method. Okay, because they will all allow you to do calibration with a checkerboard pattern or with some other, but 2D patterns. Like you can take the image or you can take a picture of that pattern as a 2D object and still do it. Okay. The point is that, well, you have this object, and now this object is a checkerboard pattern. Okay. So you have so why checkerboard pattern? Because checkerboard pattern, if you take the picture of this, okay, it is easy to, from the image, it is easy to isolate the edges and corners of a checkerboard pattern. Okay, so you don't have to stick to a checkerboard pattern. You can use other patterns also where the edges and points can be easily determined. Okay, so that is the reason for choosing a checkerboard pattern, nothing else. So now suppose you have some points here. Okay, so suppose these points are detected by your algorithm. These are on the object, and you take some number of images, okay, of the same object from various angles, the same camera and from various angles. Okay, so you will have these matching points, right? So you have capital X1, capital X2, capital X3, and so on. And then you will have here you will have one matching. So that will give you one set of equations. This pair will be one matching. This will be your small x1, small x2. Correct? The image will also be like this. Correct? Similarly, second image will give you a second set of equations. Third image will give you a third set of equations, and so on. So each time you will get a set of equations. So you have one homography here. Okay. Or what? So you need to know the real coordinates of the points. Okay. So this is like your reference. Okay, so the reference image is your real coordinates. Okay, and Zhang's method says you construct homographies from the real coordinates to these various images. Okay, so this is one homography. This is another homography. This is a third homography, and so on. Okay, so we construct these various homographies, and then using those homographies, we solve for this matrix P. Okay, so what I described here is the theoretical or the direct linear transform way of doing it. Okay, but Zhang's method is slightly different. Okay, so if there are no questions, I just want to make a little note on data normalization or preconditioning. So the important thing here is that the homography that you get using the direct linear transform that I showed earlier is not a invariant under changes of coordinate axis. Okay, so if you for the image, okay, so suppose the image center is here and your image coordinates are here. Okay, or the image origin is here. So you might want, for some reasons, to move the image origin to the image center. Okay, you might want to do this. But homography is not invariant under this change. Okay, so if you change this, then the homography changes. So fine. So we can do this transformation and apply its inverse. Okay, but making this change is sometimes very useful. It has two main uses. So this is called data normalization. Okay, and it has two main. It improves accuracy, and the result that you get is invariant under change of scale and coordinate origin. Okay, because we will apply this, do the do the computation, and come back. Okay. So the data normalization is done as follows. The chosen points are translated so that their centroid is at the origin. Okay, and then so this is probably the other way. We do the transformation this way. The points are scaled so that their average distance from the origin is square root 2. So scaling and translation of origin. Okay, and if you want to put it in terms of equations, then the algorithm in case of a homography, first step will be to compute a similarity transformation T, which consists of a translation and scaling that I just described. Okay, then you compute a similarity transformation T prime going the other way. Okay, so here T consisting of a translation and scaling that takes xi to a new set of points xi tilde, such that the centroid of xi tilde is the origin and their average distance from the origin is root 2. Okay, and now you compute a similarity transformation T prime taking xi prime to xi prime tilde in the similar manner. Okay, so what are xi and xi prime? These are these matching points. Okay. So yeah, here is this picture is clearer. So we construct a similarity transformation that takes xi to xi tilde, takes xi prime to xi prime tilde. Okay, and what we really want is a homography here. What we compute is a homography here. Okay, where these are now normalized data. Okay, so we compute this h tilde. Okay, and then to get the required h, what do? You apply this. Okay, h is t prime h tilde, sorry, t prime inverse h tilde t, the composition of those three maps, right? So that's what you do in the end. You do denormalization, t prime inverse h tilde t. And the same thing can be done in case of a camera matrix. Okay, so this diagram describes it again. You want a camera matrix P between matching points capital Xi and small xi. First, you find a similarity transformation that takes xi to xi, capital Xi to capital Xi tilde, small xi to small xi tilde, the similarity transformation U. You compute P tilde here with the normalized data, and then you can get P by applying the maps appropriately. Okay, so U inverse P tilde T. That will give you the required camera matrix P. Okay, so why do you want to do this long step? To improve accuracy. Okay, so essentially this normalization improves accuracy, and so this step is done. Okay, so that was just a remark, but I don't think you will do this data normalization by hand. I think the number of functions already do the data normalization within the function. Okay, again, that is something you need to check and make sure you want the function to do it or not. Okay, so depending on your situation, you might ask the function to do the data normalization, or you might choose not to do it. All right, so I will stop this for now. Okay, and I want to talk about removing a radial distortion. I'll do that next time. Okay, so that now, so where are we going now? So let me just outline what will be the next topic. So we want to talk about removing radial distortion. And that, once we have talked about this, that will sort of end our discussion on image formation with a single camera. Okay, so topics up to here, these were all about single view geometry. So I cannot say I have covered everything in complete detail, but I think I gave you a good view of what image formation with a single camera means. Okay. However, one of the most important problems in computer vision is about reconstruction. Okay, so what is reconstruction? Reconstruction means you have been, so this can take various forms. Okay, so at least two forms I can describe easily. So one of the forms is you are given the image of something. Okay, and from this one image, by studying the geometry of this image, you want to try and reconstruct the 3D object. Okay, so for example, there are some Renaissance paintings, and people have constructed 3D rooms, or try to reconstruct the actual object from those paintings. Anyway, so you can take a single picture or a single image and try to construct a 3D object. So this is one thing that can be done. Another and more commonly uh, used problem of reconstruction is that you have a number of views, okay, of a single scene. So you can imagine that on a railway station, for example, you have many various cameras fixed, right? So you have various views of a single platform, okay, and from those number of views, you actually determine number of things, okay, that were in 3D. For example, distance between two objects. Okay, so this is in short constructing how the actual 3D objects would have looked like. Okay, the 3D scene, reconstructing the 3D scene. Okay, for example, you want to measure the distance between objects. Okay, you want to, or you want to measure speed, which also comes down to measuring distance between objects. Okay, then so all kind of metrical measurements. Okay, so metric measurements. Okay, so this is a very common use or a very common application of computer vision, which is this is called as just reconstruction or 3D reconstruction. Okay, and the geometry that talks about this number of views, when you have more than one view of a single scene, and how to compute all this from those number of views, that geometry is called as multiple view geometry. Okay, and that is what this book is about, multiple view geometry. So of course, different number of views have to be treated differently. Okay, so what I hope to and this is also called as stereo. Okay, stereo vision. So the thing that I wish to cover is at least talk a little about two view. Okay, two views, and this is called as the geometry that lies here is two view geometry or epipolar geometry. Okay, and that is all. I mean, I don't think we will go to three view or later, because if you go to more than two views, the language of linear algebra is not sufficient. Okay, you need to talk about tensors and stuff like that. So that is one reason why we will not go there. Okay, so but this two view geometry or epipolar geometry is exactly the geometry that explains human vision. So you look at an object with your eyes. So you have two eyes, right? So with two eyes, you are looking at the same object, and your brain is reconstructing the object from this. Correct. So that epipolar geometry also explains human vision, and it's not too difficult. Okay. So just like for the single view case, we had this camera matrix. In the two view case, we have the fundamental matrix. Okay. So I will try to do this in one or at most two lectures. Okay, give you a glimpse of what is two-view geometry. Okay, and that is where we'll stop. Okay, so this will be when I finish this. This will be the end of the image formation part of the course. Okay, and then we will move go to image processing part.